So it's worth adding a little bit about the surfing, what I already mentioned. Surfing is like riding a gravity-operated water sled. I don't know. I'm just saying what the book is saying. Basically, it's easy to imagine that if you watch the position of the surfer, they are not standing straight up, right? So they are at an angle going pretty fast. So gravity is pulling on them, and buoyancy is keeping them from falling down. So they are doing this very fancy force balance they learn by doing. It's not that they calculate something, but they keep on doing it till they learn how to balance. And a skilled surfer can go pretty fast on the wave front, 40 kilometer per hour. That's pretty fast. You can imagine a car going at 40 kilometers per hour. That's going pretty fast. So let's now move on to wave refraction. What is refraction as opposed to reflection? Reflection is like when you look in the mirror, the rays are coming right back at you, so you see your own image being projected in the mirror. Refraction is kind of a bending. Okay, so we'll see examples. Waves, obviously, we said already that they rarely approach at a perfect 90-degree angle. So if you have a wavefront that's running parallel to the beach, then the wave is coming in at 90 degrees, but usually there is a little angle. It's never that perfectly parallel to the coast, right? So as waves approach, they bend, so the wave crests are trying to become nearly parallel to the shore. So if you go further out, they have a much more steeper angle, and they slowly refract to become almost parallel to the shore. So wave speed is already we said once it becomes shallow water wave close enough to the coast and the wave feels the bottom, then it's a wave speed that is proportional to the square root of the depth. So different segments of the waves are then traveling at different speeds. So you can imagine here the beach is here and the wavefront is moving along this way. The wavefront that has already come close to the beach is in a shallow topography, so square root d, so it's moving slower, whereas this one is out in the deeper part of the ocean, so d is deeper. Even though it's a shallow water wave and it's feeling the bottom, depth is greater than at the beach, because remember the beach is above the water. As you go into the water, the slopes off, right? You get deeper and deeper into the water. So square root d is greater, so this is moving faster. This is moving faster than here. So you're going to refract the wave to become almost parallel to the coast. Okay, so that is wave refraction. But the more interesting consequence of this is that if you have a wave beachfront that is not very uniform, okay, and let's say there is a little jutting out of the beach, and those are the parts that are used typically for installing a lighthouse, because you want the ships to be able to see well before they come very close to the beach, because they don't want to hit the bottom, right? They don't want to get stranded. So wave energy is unevenly distributed on the shore because of this refraction that's going on. And remember these wave crests are running kind of parallel here, and they're getting concentrated here. We will see an animation soon, and the wave is moving in this direction. So because of this wave refraction, the waves get concentrated into the headland. So this thing that is jetting out here is called headland. That's the official technical term. So more energy is dissipated, so you concentrate the wave energy here. So the erosion is faster here. If you have a wave, it's a beachfront that is already lost all the soft material and only rocky material is left, then obviously the erosion is very, very slow. But if you still have soft material, then this headland is going to be eroding faster than the other parts, okay, that are behind, the cove as it's called here. So let's look at this animation. Low wave energy deposition here at the cove on either side. The headland, which has this cute little lighthouse. You are looking at the wave motion, so the crests and troughs are coming in. They are being focused into the headland because of this square root GD business that we talked about. So if you look at the wave motion, the waves that are coming in, if you look at a cross section from the deep ocean towards the beach, we said the wave starts off as a deep water wave. In the open ocean, most of the wind-driven waves are deep water waves because their ocean is deeper than L/2. Then they transition into shallow water waves and they tilt over because wavelength gets shorter, wave speed gets slower, and wave height increases. And surely enough, as you get very close to the beach, H/L becomes greater than 1/7, then you get surf or the breaking of the waves, right? Let's look at the wave refraction now. So this is what we started with. So you are seeing these various wave fronts coming in, low energy and energy deposition and erosion, or you can even have sand being deposited that is being eroded from here and so on. Let's not get into those kinds of details, but concentrated energy here means more erosion here because all the energy is being broken. Waves come and hit the land and they break, so they deposit the energy at the coast. That's how coastal erosion happens, right? Other than currents advecting away soft material as well. Let's do something really cute here. Let's add coastal erosion and see carefully what happens. So coastal erosion is happening, and look at this. So soon, boom, the lighthouse is gone. Okay? How much time did it take me to make this animation? This is not Steven Spielberg, but nonetheless, look at the coastal erosion. Wave energy being focused onto the headland compared to the coves. Erosion is greater, so erosion begins to take away the land. You can see the land retreating. Soon enough, it goes too far, and then the lighthouse is gone. Okay, so that is wave refraction. And sorry, I have one more slide. This is the example shown as an image. So you have a bend in the coastline here, people living so close to the coast, obviously, and you have wave. You can see wave fronts coming here. So wave is moving in this direction. It's going to hit land here, and you can see the waves becoming almost parallel to the coast here, but because of this bend in the land, you can see the refracted or the bend in the waves coming around on this side here. Okay, so this is a very nice example of how the headland is going to gradually erode and deposit sediments in the bays and the coves and so on and so forth. So we'll see some examples later on when we come to coasts and beaches to see how people are getting closer to the coast, changing the coastline because of land use and land change, and how that changes where the waves break, how much energy is deposited at the coast, and so on and so forth. So coastal wave forms themselves are changing because of climate change, ocean warming, sea level rise, and then people are getting closer to the coast. So all these together, plus we are removing mangroves and doing other things to sink the land, etc. So this all going to add up to coastal erosion, right? So what can we do against that? We'll see it in a later chapter.